All right, this is the second hour of Physics 1C for March 17th, and we're going to do this one problem right here. What we have happening in this problem is we've got some bad guys 960 meters away from a hospital, so they're right here at this corner, and here's the hospital right here in the middle. Fire their mortar at 100 meters per second at 53.13 degrees toward the hospital, so they shoot some kind of a mortar in the direction of this hospital. At the same instant, some ECC physics students on a hilltop that's 50 meters tall, which is 2,000 meters away from the bad guys, fired their mortar with an initial velocity of 36.8, with an initial velocity that we don't know. This is actually what we're trying to calculate. But we do know the angle they make right here. So the angle phi, I'll just write it up here, is 36.87 degrees. And the angle theta is 53.13 degrees. All right, we're going to use g equal to 10 to make some of the calculations simpler. And our goal is to find the x and y coordinates of the impact. So the goal of this is that these people are shooting a mortar at a hospital, and the physics students are over here, and they're trying to basically intercept that mortar by firing their own projectile so that it impacts right here, and then there's some kind of explosion in the middle. And our goal is to find what is the xy coordinate of that impact. Okay. We also need to figure out this velocity over here, but then we also want to find what is the xy coordinate of this impact right here. All right. So that is the problem that we want to solve. It involves two different projectiles that are both moving at the same time, and they're both launched at the same time because it says at the same instant, which is circled here. So we know that both projectiles are shot simultaneously, and we also know that they meet in midair. That's what we know. And we know some information about each one of them, such as the initial velocity of this one and each of these angles. We also know how far apart the two projectiles start, as well as this distance, which is, I think, inconsequential. The 960 meters doesn't really matter. All right. So let's go about solving this. The first thing that we want to do is to kind of tabulate all the information that we have for each of these situations. So for the bad guys and for the students, into a table. So let's do that. So we'll start off with the bad guys over here. That's not how you spell guys. Guys. They're going to have X information and Y information. And in order to know what their X and Y information is going to be, I left a step out, we need to define a coordinate system. So we'll call this positive X direction, and we'll call this one the positive Y direction. And then we need to just start kind of filling out these tables. So in the X direction and Y direction, we're going to have information. In the X direction, we would have delta X, which we don't really know. But we could break delta X into an initial X coordinate, which we do know. We'll call that 0, because they're starting down here at the corner of the coordinate system, and a final X coordinate, which I'm just going to call X. That's going to be the place where they meet. So we're just going to use the symbol X to represent that. There's also going to be an initial velocity in the X direction, or just the X coordinate of the velocity. That can be found, of course, by breaking up this velocity here into components. Always one of the most important things to do with these problems. So let's do it. There's going to be an X component that points this way, and then there's going to be a Y component that points straight up. Like that right there. This side we'll call V sub X. This side we're going to call Vy initial. So we know what these are going to be. Vy initial is going to be equal to, I'm just calling this one V. V times the sine of theta. And Vx will be equal to V times the cosine of theta. So if we plug in the numbers that we have, Vx is going to be equal to 100 meters per second multiplied by the cosine of, what is it, 53.13. Theta is 53.13. So V sub x, I believe, is going to be 60. You all can calculate that and tell me if you get the same thing. And then there's t, and we don't know what time is in this part. Okay, 4860. Okay. All right. Now we want to do the y direction. Just use a little bar here to separate what we're doing. There's going to be delta y, which we don't know. We just know that they meet at some point. There's going to be y initial, which we do know, which is 0. There's going to be y final, which is what I'm just going to call y. There's going to be vy initial, which is going to be equal to 100 times the sine of 53.13. And if you calculate that, you should get 80. And then we're going to have things like v final or vy final, which we don't know. And we'll also have one more variable, which is t. One more after that, which is the acceleration in the y direction, which is going to be negative 10. So that's all the information for the bad guys. We'll probably simplify all this into a more readable format in the next step. Let's start working on the other pieces of information we have. So over here we have the ECC students that are trying to save the hospital. And they will also have X and Y information. Similarly, we can figure out what that information is going to look like by taking components of this initial velocity vector. So the X component goes back like this. And the Y component points upwards like this. And we'll know that this side over here is going to be equal to v initial times the cosine of phi. And this side over here is going to be v initial times the sine of phi. And I'm just going to go ahead and say that this one is going to be negative because they're shooting it to the left and our positive direction is to the right. I should probably start with delta x a little more to the left here. Trying to save some room in the middle here that we can maybe write some equations down. We'll see. So we're going to have delta x, which we don't know. But what we do know is x initial. What's x initial equal to? $2,000. It's given right here in the problem. They start off 2,000 meters away. X final, they're also going to end up at the same coordinate x, so we'll just call that x. V sub x, well, we don't really know what v naught is, so we're just going to write negative v naught cos phi. And the final variable would be t, which we also don't know. Okay, now we can do the y direction. In the y direction, we've got delta y, which we don't know, but we do know y initial is equal to positive 50. And y final is going to be what we're calling y, the final location of impact right here. And then we've got vy initial, which is going to be positive v naught sine theta, or sine phi, sorry. This guy right here. Vy final, we don't know that one. We don't really care about it. Acceleration in the y direction is also negative 10. And time, which we don't know. All right. You might wonder why I put t equal to question mark in every single bit of these. And it's mostly because, in general, I'd like to be able to look at any one of these subsets. Because each one of these we can produce equations for. X direction is one equation. Y direction is one equation. There's 4 equations that we can really write down here with this information. And if it's possible that any one of them can tell us information about time, I'd like to know. So if we look over the information we're given, unfortunately, there's too many unknowns. There's just too many unknowns, basically. No one of these sets of data is complete. So for example, this one's close. We know the initial x coordinate. We don't know the final x coordinate. We do know the x velocity, but we also don't know time, right? And the equation we would use here would be delta x is equal to vx times t. And unfortunately, we don't know delta x and we don't know t, so we can't really find any relationship between the two of them. Likewise, if we look at the y direction here, we've got vy initial, we've got acceleration, but that's all we have. For each one of these grids, there are 2 pieces of information given in each one of them. and so there's a lot of unknowns. Specifically, the unknowns are x, y, and t, along with final velocities, but we're not really going to care about those. All right. So now that we have all of our data tabulated, we are going to start writing down equations to relate all these variables to each other and see if we can't come up with some way to solve for what's happening in the problem. Oh, I was wrong. There's 4 variables, right? Let's write up here what the unknowns are. So our unknowns are x, y. This is the point of impact. That's what I'm calling those. The time at which the impact occurs. And what's the other unknown? The initial, right. The velocity at which these people are shooting. So with 4 unknowns, we need 4 equations. Luckily, we're going to have 4 equations because we have 1 from here, we have 2 from here, 3 from here, and 4 from here. That's 4 equations, right? And those 4 equations should allow us to solve for all those unknowns. Are we going to need all of them? I don't know. Sometimes you do, sometimes you don't. Let's see. Because if we could find if we could find 3 equations that only had x, y, and t, for example, then we can actually solve. All right. So we want to write down equations for each of these situations, right? So let's go through and let's do that. I don't know if we'll be able to fit all of them in here, but we'll try. We'll definitely have to move down. Let's just kind of box off this area. All right. So let's throw together these equations. So let's use the bad guys first. This is one equation that we can write down for the bad guys. We can write that basically x final minus x initial should be equal to Vx times t. And something's going to start happening here where we've basically used the same variables on the left as we have on the right. So we really are going to have to deal with that. We can either deal with it by using different colors to write the different expressions and then plugging in numbers, which might work. I don't know. But I think the easiest thing to do is just to come over here on the students and just put a prime on everything. Like this. The times are the same. We don't need to do it for that one. That's whatever. I guess this is fine. I guess we can put primes on these. Prime. Prime. There we go. Now we'll have different variables for each one of them. All right. Okay. So that equation, what else do we know about this equation? Well, we actually have some information about this one. First of all, we know that x initial was 0. We don't know what x final is, but we're calling it x. So this equation can be written as x is equal to Vx times t. I think Vx is 60, right? So this is going to be 60 meters per second multiplied by t. So there's one equation that we can use. It relates x and t. All right, let's write a y equation down. Let's put a little line between these. In the y direction here, the equation that we want to write down is going to involve delta y, Vy initial, time, and acceleration. That is this equation. Delta y is equal to Vy initial times t plus 1/2 acceleration in the y direction times time squared. And we know what some of these variables are. Delta y is going to be basically just y minus 0 because y initial is 0. Vy initial we said was 80 times t. And then 1/2 of a. So a is negative 10, right? So what's 1/2 of a going to be? It'll be negative 5, right? So okay, if I just skip that step and just write 5 here. Save a little screen space. And there we go. That's another equation. And I'm just going to get rid of the 0 here because we don't need that. Y minus 0 is obviously y. All right, there's another equation. Maybe we can at least fit all the equations on this picture. Oops. Let's draw that in black. Select. All right, got those 2 equations. And we just want to do the same thing for our ECC students over here. So we'll go through the same kind of process. Now this is going to have more variables in it, but that's fine. I guess one thing to ask is, do you all want to actually plug in what cosine phi and sine phi are? they're just numbers, right? Maybe we should. I think if you put into your calculator 36.87, what you're going to get is that cosine phi is equal to 4 over 5, or we want to write it as 4/5, or want to write, let's write it as 4 over 5. So this is going to be 4/5, and sine phi you're going to find is equal to about 0.6, which is 3 over 5. So we will plug those in when we do this. I'll write them like this first, but then we'll plug in. Okay, so in the x direction, we're going to have delta x, we're calling it prime, is going to be equal to vx prime multiplied by t. The times are the same. This equation then will become, so it's x final minus x naught, right? So it's going to be x, we're calling x final, minus x naught, which is 2,000 meters, should be equal to, I hate it when it does that, equal x minus 2,000, that's what delta x prime is going to be, final minus initial, should be equal to vx prime, which is negative, the negative sign is important here, negative v initial times cosine phi, and then we multiply by t. Let's plug in the cosine phi, and we're going to move the 2,000 to the right-hand side of the equation, so we're going to get x is equal to 2,000 meters minus v naught. Cosine phi is 4 over 5, so we'll multiply by 4 over 5. And there's going to be a t in there. All right? Got that equation? Why does it do this? I click here. There we go. Let me underline that one. And then we do the same thing for the y direction. I'm going to stop for just a second because I've done a lot now. I haven't stopped to see if anyone has any questions. Does anyone have any questions? Okay. Finally, we do the y direction. So we'll say this should have been delta y prime. So we're going to say delta y prime is equal to vy initial prime times t plus 1/2 ayt squared. Plugging in, delta y prime will be y minus 50, final minus initial. Vy prime is v naught sine theta, or sine phi. Times t, and again minus 1/2 of 10, so 5 t squared. Going down just a little bit. We're going to move the 50 to the right-hand side. So we're going to get y is equal to 50 meters plus sine phi is going to be 4 over 5. So this will be v naught times 4 over 5. Oh my god, why does it always do that? I'll answer your question in a second, Tom. 4 over 5 t. Oh, this one's 3 over 5. Yep, thank you. There we go. And now that we have used all of our physics knowledge, we can combine all these equations together. Your question was, why is delta x prime equal to x minus 2,000? Okay, so this is the important information here. So basically, in general, I think I can write this down here, delta x prime should be equal to basically x final prime minus x initial prime. And we're saying that the final coordinate of this projectile that's launched from the right is going to be x, so that's x final. And the initial coordinate of it was 2,000. And in case that wasn't clear, it's because of this distance right here, Ton. No problem. Okay. So we need to combine these 4 equations together. The first thing to ask is, do any two of them only contain two variables? Or do any three of them only contain three variables? Like, is there any two equations that just have x and t? I don't think there are. I think they all have four variables. Or they all have two or three. And there's no combination of three of them that only have three variables, right? Unless I'm crazy. Oh, maybe this one, and this one? Nope, because this introduces y. Nah, we need to use all four, basically, right? Yeah, unfortunately. I don't know if what I was asking there was super clear. But that's right, Chris, exactly. That's what we'll do. We'll set x equal to x. So we're going to set this one equal to this one. And then we'll set y equal to y. And just to save a little time, we're going to do that with just a little copy-paste. So we're going to take this one, copy, paste, and we're going to take this one, nope, not that one, the other one that's equal to x, which is this one. We'll copy, click, paste. So these should be equal to each other, right? Because those are both our x-coordinate equations. And I'm gonna move this up to where we can see everything at the same time. But we're gonna basically get two equations out of our four equations here. Okay, so this is the x equal to x equation. We'll just write that above it. Certainly a true statement that x is equal to x. And next we will do the y equal to y equation, which will be this whole equation right here. Copy, paste. This also helps to save my hand from cramping too much, because the longer I use this... Oh wait, is this gonna... Yeah, unfortunately, it's gonna be both of them. I just want... Let me get rid of this click thing somehow. It's not going away. There we go. Nope. What if I start here? There we go. Oh my god, what is it doing? Alright, I'm done. We're just gonna write it out. I don't know what's happening right now. Alright, so 50. Oh, look, it's just gonna start moving things now. It's not even gonna let me. Ooh, that did it. Okay, maybe we can do this again. Let's try. One last try. Copy, paste, boom. There we go. So those are the equations we want to solve. It looks like we lost a parenthesis here. We can put that back in right there. All right. So the equation on the left over here and the equation on the right over here, we're down to just two variables now that we can solve for. So we really want to either solve for the time and plug it in to one of the equations, or we want to solve for the initial velocity and plug it in. And it's really up to you how you want to do this. T is really, well, I guess we could do T. The problem with solving for T is that T shows up as T to the first power and then it's T squared. So we're going to have to do some squaring, and it will work. But yeah, you immediately see that that's going to be a little bit more tricky. So at least with V naught, we only need to replace just that one term right there, right? So let's use this equation. Let's solve for V initial. And yeah, we'll go from there. All right, so we'll do the rest of this in black. So we've got 60t. I'm gonna leave all of the units in. I'm sure probably a lot of you don't do this when you're doing your homework, which is, you know, it's fine and all, but I think for this, I need to at least include the units. For me, it helps keep track to make sure that I don't make a mistake, honestly. Oh, that's not the way that I want to do that, because the negative sign. So let's add this one to the left side and subtract this one over here. So on the right side, we'll get 2,000, subtract this one, minus 60t, should be equal to 4 over 5 v initial times t. And now we just need to divide 4/5 t to the right-hand side. So we'll get v initial is equal to 5 over 4 and we also need to divide by t. Now, the t, I think, it's just going to cancel out with this thing over here, but I will divide the 4 through here. So we're going to have, I'm not going to multiply the 5 through, as for what reason it'll probably become pretty obvious in a second. 2,000 divided by 4 is 500. And 60 over 4 is 15. And you know what, we'll just put the 1 over t at the front. Which works just as well. Okay, so before I sub this in, I just want you all to check to make sure this is actually right. Because I don't want to jump to the next step and do a bunch of algebra if it's wrong. Everything look okay there to everyone? Let's go through each step just to check. We subtracted 60, it became negative. We added this one, it became positive. And then we multiplied by 5 over 4 to eliminate this. It shows up over here. We divided by t. And then we multiplied through by 1/4. 2,000 over 4 is 500. 60 over 4 is 15. Yeah, looks good. So now we got to plug it in for V0 right here. And it might look like that could get really messy, but it's actually going to simplify quite a bit. Oh, there's another simplification we can do even before we do that, actually. Which is this and this are the same. So they disappear. So what we have is 80 meters per second times the time is equal to 50 meters plus the initial, which is all of this stuff, so that's the initial. All of that. Multiplied by 3 over 5t. Now some things will cancel out. So this t will cancel with this t, and this 5 will cancel with this 5. That's why I didn't multiply the 5 through. So we have, on the left-hand side, okay, so what's left inside of here? We still have a 3 multiplied to everything, so we'll do that in the next step. So 3 times 500 minus 15 meters per second times t. We just need to multiply that all through, and then just group our terms. We actually solved this problem much faster than I thought we did, than I thought we would have. Okay, 3 times 500 is 1,500. And 3 times negative 15 would be negative 45. Now we just need to add this one to the left-hand side. So 80 plus 145 should be 125, I believe. So again, this is why I'm keeping these units everywhere. I know that when I add these together, they have to be the same unit. When I add 50 and 15, they have to be the same unit. So just checking to make sure that I'm not doing anything silly. Because personally, what I do a lot is I drop t's. Because the t looks just like a plus sign, unfortunately. So it's very common for me to just accidentally drop a t. And if I was doing all of this with just symbols, I might mess up. But I know that anytime I have a speed, it needs to be multiplied by time because all the other terms are in meters, right? And when you do meters per second times seconds, you get meters. So it's okay to add that kind of stuff. So in case you're wondering why, you might think it's just a big waste of time to write all these units and stuff like that. It really, for me, it helps me to keep track of the math and to help me to prevent myself from making mistakes because I am very prone to make mistakes personally, as I'm sure all of you are as well. Some of you may be just gods at math and you never make mistakes, but someday that will change. Someday you will eventually take a class that is hard enough that the mathematics will, that your gift with mathematics will no longer carry you through. All right, looks like we got an answer in the chat. Sounds like the answer is 12.4. More than one person says it. Seems reasonable based on these numbers to me. So 1550 meters divided by 125 meters per second. That should be equal to our time. And everyone's saying that it's 12.4. My memory is that that is the correct answer, as far as I know. you have a homework problem in your lab manual that is almost identical to this, except it's a little easier because in the one in the lab manual, I'm pretty sure that the angle phi is 0. So you have a very similar setup, except this projectile is launched straight, basically, which simplifies some of the math. It still takes a lot of work. Now, we're not done, because we need to figure out the x and y coordinates as well. Now, all we need to do then is to use these equations here. X equal to 60t will tell us what the x coordinate was. So x is equal to 60t. That was one of our original equations. So x equal to 60 times 12.4 meters, seconds. Hopefully you all calculate what that is for me. And then for the y direction, we'll use this one here. Y is equal to 80t minus 5t squared. So 80 times t, which would be 12.4, minus 5 times... Is that really the answer? 74.4? 744. Yes, that I can believe. 744 I can believe. Thank you. What we're doing, 80t minus 5t squared, so 5 meters per second squared, times t squared, which is 12.4 seconds squared. That one is going to be 223.2. X, Y, and T, what we were looking to solve for. Oh, we have one more variable, didn't we? This one, initial velocity. So, initial velocity should be equal to 5 divided by t times I get 126.6. There we go. We just had to solve 4 equations with 4 unknowns. It takes a little bit of algebra, a little bit of organization, but, you know, there it is. Anyone have any questions? That's a really long problem. We can zoom out to see just how long it is. Look at all that math we had to do. Yeah, physics is pretty challenging. Because if you mess up, if we messed up anything in any of this information, if we had a minus sign somewhere that was wrong, if we did like I did, and I think the first time that I wrote this one down, you all caught that it was, I think I wrote 4/5 and it was actually 3/5, because at the time I was scrolled down to where I couldn't see what I wrote. I don't know, if I left off a minus sign here, if we didn't realize that this should have been negative right here, right? Any one of those things would have thrown the whole calculation off. It's a very kind of delicate balancing act to make sure. Yeah, 2 full pages in your notebook, great. So, anyway, good problem though. Definitely challenges your understanding of projectiles, and if you can do things like this, then you can do anything. As far as projectiles go, at least. Next chapter, we'll start doing some Newton's law things. That's what we have next week. We're going to start with Newton's laws. And we're going to mostly be talking about Newton's second law and using it to solve problems. So if you want to brush up on that, you can. You can start looking at some of the problems that show up in the example packet, which, again, the example packet is on the Canvas page, And what we'll be doing next time, I don't know why it does that every time. Projectiles, we just finished that. Newton's second law is next. So if you want to prep for next class, honestly, you could probably get away with just reading this. And maybe trying to do a few of these problems. I will say, like, these problems get really, really hard. These last 3 problems right here, they are super challenging. So if you were really good, the last time you took physics, if you were really good at solving Newton's laws problems, which is basically objects that are moving with constant acceleration and you're trying to find forces, then you might want to pick this packet up, download it, and start thinking about these problems over here on the right, because you're going to see problems like this in your lab manual, and they are very hard. I will show you how to do all of them. But you will understand better if you've taken some time to think about them. It's not just these ones, too. I think number 6 is pretty hard. And these 2 are pretty easy. I think number 7 is kind of tricky, too. But we already did a problem like this in the past. I think 5 can be tricky for people. 4 can be tricky for people. These first 3 are kind of like confidence building. But then, yeah, these other ones get really challenging. So, especially this one right here. These last 2. Pretty hard. So anyway, that's the plan for next week. We'll stop for today. I will stick around if you still have questions about lab manual problems or your mastering physics homework or anything like that, let me know. I also, by the way, did I tell you this last time? I probably did. That I moved all of the mastering physics assignments to be due on Monday night instead of Fridays. So you should have like a lot more time to finish them up. So this projectile assignment I think is due on Monday night. So you have you basically have 5 full days to work on that. So hopefully that's enough time. Yeah. I'm gonna stop the stream, but like I said, I'll stick around and answer any questions anyone has. But otherwise, you're free to go and